For the second question, we want to take a look at this graph that is presented to us and solve a series of different limits, derivatives, and point values based off of the indicated points. So looking at the first one, as it is the limit of as x approaches to -4, note the plus sign at the top. That says that we're coming from the right-hand side. So if we were to come and go down this way, that would be incorrect because we need to be coming from the right-hand side. So with that in mind, we are going to instead erase that and go from the right towards -4. As we get closer and closer to -4, we notice that we tend towards the asymptote at infinity, and so our answer is infinity. Looking at the next set, we say f prime of 8. So f prime, anytime we see prime, we're thinking derivative, we're thinking rate of change. So if we come over to 8, we're looking at the rate of change at 8. So that would indicate that we need to take a slope for this line because a line has constant slope. So taking that, we see it has a rise of 1, a run of 2, and we know the slope is then 1/2. Looking at the next one, we say the limit of as x approaches 5 from the left indicates again that we should check which direction we're coming. As we go this way towards x equal to 5, we see that we hit the point right here, y equals -1. Going to the next one, we have the integral from -8 to -6 of the function. So the integral we can think of as the area under the curve, so we need to mark out our two x positions, the first one being x equals to -8, and the other is x equals to -6. By geometry, we know that this is a rectangle, so the area is going to be the length times the width. The width in this case is our x, so we have a change of 2, and we have a height overall of 2, meaning our area is going to be 4. If we look at the second one, in the second row, we have the second derivative of x equal to, evaluated x equal to -5. So we would need to come into our x equals to -5 point. Let me erase our box here. So x equals to -5 would be right around here. And we can do some work off to the side to figure this one out, to say that we know that f df dx, in this case, would be the slope, and we can say the slope, and this is going to be something around maybe -3/2. That's just an approximation. But if we took another derivative of this, the derivative of a constant, we know, is 0. Therefore, the answer to this one is 0. Moving to the last one on the second row, we say that we're taking the limit as delta x approaches 0, f of 4 plus delta x minus f of 4, and over delta x. If you remember from early in the semester when you are looking at the definition of the derivative, this will look relatively familiar. This is just saying to take the derivative at f of 4. So we come up to the graph, we find f of 4 right here, and we say the slope at that point, since it's a minimum, is horizontal. So the slope is 0. Looking at the bottom left corner of our questions here, we see that we're looking at what appears to be another slope. Notice this one does not have a limit, so we're not looking at a derivative. We're just going to look at the average rate of change. Plotting our 2 points as x equals to 7.3 and x equals to 6, we get points that are something along the lines of right here and here. Since they're on that same line that we did up above for f prime of 8, we know right away the slope of that is going to be 1/2. So, continuing along with this one, we say the limit as x approaches to -infinity. That means we're just going to look over here at the leftward tendencies of the graph. As it becomes horizontal at this point, we know that it needs to be it's going to continue to approach 2 for all time. So the answer is 2. F double prime of 0, to round out this section, is the second derivative at 0. So if we look at this region of the graph, we can make a note that on the left-hand side, we're concave up. On the right-hand side, however, we're concave down. Since we're switching from concave up to concave down at this point, that is an inflection point. Important to note is inflection points have a second derivative value of 0. They're like critical points, but for the second derivative. And so we've rounded out that entire section. The last little bit is to identify a value for x for which f is continuous but not differentiable. So what we need is there to be a different slope from the right-hand side than from the left-hand side. A good candidate for this one is to take a look up here at the area that I'm erasing so that we have a little more room to work, and to say that we have x equal to -6. Because notice on this point, if we came from the right-hand side up, we'd have a slope that's negative. But at the same time, the slope from the left is horizontal, or 0. So that means that we have an issue here where we are continuous, there is a value at -6, but there's no slope that we can get from it. So the answer is x equal to -6. Looking at the next page, we have a continuous function y of f of x defined over the interval of 1 to 2. We have a couple of properties that are given to it as well. We're saying that we know f of 0 is 3, f prime of 0 is 0, f double prime of -0.8 is equal to f double prime of 1, which is equal to 0. So with all of this information, we have to draw out some key points. I think it's easiest to start at what we know about the function itself and then work with the derivatives after that. So we know that there's a point at 0, 3, and that comes from this guy. So we know we have 0, 3. And we'll mark that out on the graph at 0, 3. The next thing we know is that f prime of 0 is equal to 0. And we know that the f prime of x is greater than 0 on the interval to the left of 0. So that would tell us that this is a critical point. We know that to the left, since we're greater than 0, we are increasing. And just below it says that we are negative on the interval to the right of 0, so we would be decreasing. The next step tells us that we've got f double prime of x greater than 0, which means that we're going to be concave up. And that's on a section of the interval to the left, as well as a section of the interval to the right. So we'll put a little note of concave up. And the bottom one tells us we are concave down over a section of the middle. So I'm going to come in here with with a little bit different color marker and kind of put some of these lines down for us. The first one that I'm going to work with is the increasing and decreasing. So we know that everything bounded on the left-hand side by this red line and this red line should be increasing. Likewise, that middle red line and the blue line out at 2, everything should be decreasing. So we've got increasing and decreasing. The next thing we say is, okay, we know that f double prime of x between -1 and 0.8, so right around here, is going to be greater than 0. We're concave up in that region. Additionally, to the right of it, in between that point and 1, we are concave down. So I would say we should expect something to be looking concave down that's increasing up until our maxima and decreasing, pardon the slight bump, something like that. We know on the left-hand side, again, we said increasing and concave up, so we could draw something maybe like this. And we need something decreasing and concave up, so we draw something maybe like that. Maybe a little less flat at the end. And that's all we have to do. We double check it just to make sure that we do have our first point, which is 0, 3. We have our critical point right there. We have our inflection points at 1 and -0.8. We're concave down throughout the middle region and concave up on the edge regions. And we are off to the races.